Hi everybody. We're going to look at the fundamental theorem part 2, or it's basically a special, not everyone calls it part 2, but it's basically a special case when we're finding the derivatives of integrals. So let's get in the box here. I've got some information that's given to you. It says let f prime equal, big F prime equal little f. What that means is that f is an antiderivative of little f. So we're going to kind of look at this as, hey, if I take the derivative of big F, I get f prime, and we're going to call that little f, right? F prime is little f. And then f is an antiderivative. Big F is an antiderivative of little f, which means if I were to integrate little f, I'm getting back up here to big F. So what about derivatives of integrals? Well, generally, we can use the fundamental theorem and kind of look at this. If I'm taking the derivative of an integral, let's integrate first. Okay, I'm just going to integrate, so I'm going to leave this derivative just kind of hanging out there. If we integrate little f according to this, we get big F. And we will be responsible for evaluating it. I haven't taken the derivative yet, so it's just hanging out. So we're going to get, and we're going to let a here as a constant, just like it's been in our past videos. We're going to plug in the upper bound, big F at x, minus what we get when we plug in the lower bound. So if a is a constant, then a function evaluated at a will also be a constant. So look what happens when we take the derivative here. Well, I know that the derivative is big F is f prime, and the derivative here of a constant is 0. And then if we remember, this has been said that f prime is little f, which is kind of interesting because it works kind of like what you would think, right? That if we take the derivative of an integral, we're going to get some form of what we started with, right? It's like adding, subtracting, or multiplying and then dividing by the same number. You get very close to what you started with in this case. Okay, so let's go ahead and guess. What do you think we'll get when we integrate sine and then take its derivative? Now, a logical guess would be you'd end up with something sort of like itself. And let's go ahead and see if we can actually do that and prove that our guess is pretty logical. So I'm going to take the derivative of sine. Okay, so let's integrate it first. If you integrate sine, you get negative cosine, right? Derivative of negative cosine is positive sine. And then we'll plug in some values. Upper bound minus the lower bound, which is minus a negative cosine 0. Okay, and then we're going to look at this here. I'm going to make this a negative cosine x, and then I'm going to have this be a plus, right? So cosine at 0 is just plus 1. And now we have still not taken the derivative. So let's take the derivative of negative cosine, which is sine, and the derivative of 1, which is 0. So I mean, it looks as though we have something going on there, right? That we've got the basic idea, but we need to do some revision, and I'm going to prove it to you, okay, that we do. So if we were to guess in this case what the derivative of this integral would be, and we guessed that it would be kind of, it looks so similar to up here, why not guess sine x again, right? Okay, so maybe our guess will be that this looks like this is going to come out to be sine x. And let's just see if we're right. Pretty much told you we're not, but let's go ahead and look at why. It's one of those most important derivative rules we've got. So let's go ahead and check it out here by actually integrating and then taking the derivative. So if we integrate sine t, we're going to get negative cosine t. That's just kind of what we did last time too. We're going to evaluate it on these bounds, and maybe some of you can see what's going to happen when we take the derivative right now with the upper bound minus the lower bound. And of course, we'll make this a plus. Okay, and now let's look at what's going to happen here when we take the derivative of this. I guess I don't need that. I'll just write it in again since I got the space. There we go. Now, when we take the derivative of negative cosine x squared, we're going to get sine, inner function unchanged, times the derivative of the inner function. This is the chain rule. This is what makes the second part of the fundamental theorem happen for us, okay? That's the chain rule. And then over here, this is not a constant anymore because we plugged in something that wasn't constant up here. We plugged in an actual, mini function. So I'm going to go ahead and take the derivative of cosine, which is negative sine, inner function unchanged, then times the derivative of the inner function. Okay, so let's clean this up a little bit. I'll do 2x sine x squared, 3 sine 3x, right? Okay, so that didn't come out quite as simple as the first one. But if you look at it, both of these do have the sine function in them, right? And if we look even closer, you'll see the pattern. So I'm going to revise the rule for us, and then we're going to look at this quickly, how to do this the quick way. So what I did here, instead of saying integrating from a to x as I did in the first one, way up here, a to x, a constant to x, I made a note to myself that these weren't constants. They were little mini functions. One function in terms of x, another function in terms of x. And so when we revise this, what we're going to do is look at it as we are going to get some form of what we started with. We're going to get the function value with the upper bound plugged in times the derivative of the upper function. And then we're going to subtract what we get when we plug the lower function in times, thank you, chain rule, the derivative of that lower bound function. And let's just go prove that it's right. Let's do number 4 up here using this. Okay, so we're going to take, we said this was wrong, no sense guessing. Okay, so for 4, if we use this formula, we're going to basically just say keep your function f and plug in the upper bound times derivative of the upper bound. So our function is sine, let's plug in the upper bound, times the derivative of the upper bound. And then you're going to subtract what you get when you just take your same function f, plug in your lower bound times derivative of your lower bound. So let's go ahead and try it. Sine, plug in our lower bound, 3x, times the derivative of our lower bound. And you can see already we're right on it, right? We could clean it up a little bit, but we could have saved ourselves, all this work by just knowing this little formula. So it's very simple when we're evaluating this. We're just going to keep our function the same because we're derivative of the integral. We'll get some form of what we started with. So it'll be the function we started with, plug in the upper bound times the derivative of the upper bound, minus the function we started with, plug in the lower bound, times the derivative of the lower bound. Let's try one more, do this the quick way, and then I'll end this video for us. Okay, so let's use, let's see if I can get that up there. We will actually use the Fundamental Theorem Part 2, our new and improved, revised, going to get it right every time you're taking the derivative of an integral, right? This will help it. This will do that. So you look for this special case, and when you do, you remember this formula, or you have it jotted down, right? Okay, so we're gonna, and this is, what's the thing about this is we don't even know how to integrate this yet. We couldn't do this the other way like I did with the sine, because we knew what the antiderivative of sine is. I don't know what the antiderivative of that is. We could guess that probably all day long at this point. So we can't do it by hand. So we can only use the formula. So remember the formula. We're gonna get some form of what we started with. So we're gonna take our upper bound and plug it in. So we're gonna get natural log x squared times cosine of natural log. So I plugged in the upper bound. Now I'm going to take the derivative of the upper bound. Derivative of natural log of x is 1 over x. Done. Minus, or done with the first part. And then we're going to do the same with the lower bound. Plug in the lower bound for t. So that squared times the cosine of that, and then times the derivative of the lower bound, which is 2. and you're done. We could not have done that one by hand the long way. So it was real handy that we had this fundamental theorem of calculus extension for special case for taking the derivative of integrals. All right, that's it.